Welcome back to this course on Fundamentals of Computer Architecture. In this lesson I will start a new module, Review of Caches. In this lesson I will review caches and the principle of locality. As usual, here are the objectives for this module. I expect you to be able to explain why a memory hierarchy is needed in modern computing systems. Furthermore, I expect you to explain the following terms which are listed here: cache, locality, cache hit, cache miss, etc. I will not read all these terms to you. You will see them when they are passing by on the slides. Here's a motivation for the memory hierarchy. In the 5-stage canonical pipeline, we assumed that both instruction fetch and the memory access stage, both IF and MEM, take one clock cycle. Unfortunately, this is an unrealistic assumption because the latency of memory, which is usually implemented using dynamic random access memory, has decreased much slower than the processor cycle time. This figure here illustrates the processor memory performance gap. It shows the relative performance since 1980. Here are the years, horizontally are the years, vertically is the relative performance, assuming that the speed in 1980 of both was 1. We see that processor speed has increased much more than the DRAM speed, right? Notice also that the y-axis is on a logarithmic scale. So what looks linear is in fact exponential. How do we solve this problem? We need to load data from memory, we need to store data to memory, and this should not hurt our performance too much. The simplest solution we can think of is to use a faster memory. Faster memories can be built, for example, to use SRAM technology, static RAM technology instead of DRAM. However, SRAMs are less dense, meaning they occupy more space and more costly in terms of DRAM. The second approach, and that's the approach I will discuss in this lesson, is to use a hierarchy of memories. The idea is to place an SRAM cache on the same chip with the execution unit. And the SRAM cache should contain code and data, instructions and data that is often used now and in the near future. So that gives rise to this picture here. On the right we have the chip with the CPU and the registers, and on the chip is a cache which is limited in size, for example 64 kilobyte, but has a cycle time 1 nanosecond in this example, an access time 1 nanosecond in this example, which is close to the 3 gigahertz clock of the processor, which is also the access time of the registers. Then main memory is much larger, orders 1000x larger, 4 to 16 gigabyte, excuse me, a factor of million almost larger, but the access time is 50 to 100 nanoseconds, meaning in that time we can execute 150 up to 300 instructions. And at the end, at the bottom of our memory hierarchy, we have disk storage, which is huge in size, which is relatively cheap, but which has a huge access time, and I will get back to disk storage when I discuss virtual memory. Why should this work? Why do we think this would be a good idea? Caches exploit locality. Programs have locality. There are two forms of locality. First, temporal locality. That means that if an instruction, if code or data has been referenced, then it is likely that it will be needed again very soon. For example, code in a loop or scalar accesses to a scalar inside a loop, right? For example, the instruction implementing x, or the instructions implementing xi becomes xi plus s, that's a form of temporal code locality. The second reason is spatial locality. Spatial locality tells us that if code or data is referenced, then it is extremely likely that code or data that is close by, that is adjacent in memory, will be needed soon. For example, the instructions in a basic block, or scanning all elements of an array. Okay, we now know more or less what a cache is. What are the fundamental cache questions? What are the top level questions, the high level questions? The first one is, when do we bring contents of memory into the cache? The second question we're going to try to solve in this lesson is, where do we put it in the cache? And the third question we try to solve in this lesson is, how do we know it's there? Going back to the first question, when do we bring data in memory, contents of a memory location into a cache? The simplest answer, which we will relax in later lesson, is on demand. When we need information that is not in the cache, we fetch it from memory and put it in the cache. Here's an example. Here's our CPU with an on-chip cache, and here's big memory which contains information, a data word D. Now the processor reads D, right? D is not in cache, therefore we call it a miss. However, the memory returns D from memory, and we put D in the cache, so the next time we access D, it will probably be a hit. Then we read D again and again. Because D has been brought into cache by the previous read, we will find D in cache, and that corresponds to a cache hit. The second top level question was, where do we put it in the cache? There's a long answer and there's a short answer. The short answer says it depends on the cache organization. I will discuss different organizations of caches, but the simplest organization is to have a direct map cache. That means that every block of data or block of instructions in memory maps to exactly one cache block. This is illustrated in this example. All the red blocks in memory on the right-hand side map to the same cache block, the same cache position in cache. This completes this lesson. Thank you for watching. In the next lesson, I will describe the organization of direct mapped caches. Hope to see you back.